Funding for Current Conversations is provided by University of Oklahoma President's Office, University of Oklahoma Outreach, and World Literature Today. Welcome to Current Conversations. I'm R.C. Davis-Undiano. Today we're going to be talking about the weather and the scientists who are trying to do something about it. The meteorologists who are predicting the weather, changing their technology, and possibly in the future, changing the way we understand the weather. To talk with us about these issues today, we have Dr. Harold E. Brooks, who is Senior Research Scientist at the National Oceanic and Atmospheric Administration Severe Storms Lab, and he's also a scientist affiliated with the University of Oklahoma School of Meteorology. Now, is it just me, or is your area just changing at an incredibly rapid pace? The technology and what you all do?
Well, it certainly seems to me like we change pretty quickly most of the time. Sometimes it seems like we change pretty slowly, but certainly over the course of the 25 years I've been in the field, things have changed an awful lot.
Well, you talk about the 25 years you've been in the field. Could you take us back 25 years ago? What was it like? What were the main steps of predicting the weather, and how good was it 25 years ago?
Well, in some sense, the steps that we take to predict the weather haven't changed very much, but a lot of the tools we have to make those predictions have changed a lot. When we think about the computer models that we run, that we essentially solve the equations of motion that we use to make the basic predictions, 25 years ago, for what we call the short-range models that are looking at maybe out to 48 hours, the horizontal grids that we used in them were more than 100 miles across. Now those grids actually in some cases are down just to a couple of miles, and so we actually can see things a whole lot better.
I'd like to understand this just a little bit better. When I hear somebody say there's a 70% chance of rain, I imagine a room with 10 guys and 7 of them raise their hand and 3 of them say, no, it's not going to rain. I mean, how do you get those percentages?
Well, there's a lot of different ways that we can define the probability of precipitation, but the National Weather Service definition is actually at any location within the area, and we have to define the area well, and we have to define the time that the forecast is valid for. But out of that area, at each individual point in there, there's a 70% chance that it will rain on that day. You can also think of it as the area that'll be covered within that forecast area. Now, to get it, we use the models, and we use a lot of statistics that say, well, historically, when the models have said this, we can interpret that as actually rain occurred when it happened. And it turns out that the models and the human beings interpreting them are incredibly, what we call, reliable at that. That when it says 30%, it happens 30% of the time. When they say 70%, it happens 70% of the time. And in fact, they're so reliable that when they first published the results in some of the decision analysis journals, the paper was actually rejected because the results were too good, and that no one was that good at judgment.
Now, you're talking about something very, very impressive. Now, was it that impressive 25 years ago, or is that where it is right now?
Absolutely. In terms of the when we made the predictions, they've always been very reliable, back even into the 70s. What's really changed is how far out we can do that. Back, if we look back to 25 years ago, we're now basically able to make forecasts that say on 3 days in advance that are as good as they used to be 1 day in advance, and that's a huge improvement for what we can do.
Is there one area of technology that has really gone forward that's made that difference? Radar, for example?
Well, radar, I think there are really two, and radar is one of them.
Okay.
Back in 1990, that's actually just before the deployment of the Doppler radar network in the United States. So we had radars that essentially were independent of each other. You'd have a radar, say, in Oklahoma City, and there'd be another one in Tulsa, and all they would actually look at was the local area they were looking in, and it was very difficult for someone to look at a radar that wasn't right at their place. And they also didn't have any information on the velocities within side of a storm that they could see. The big thing about Doppler radar is we can actually see how air is moving towards and away from the radar. And that's huge, particularly for making warnings of things like tornadoes. But the other big thing about the Doppler radars is that they're actually a network of radars, to where it's just about as easy for me, say, to look at the radar here from the Oklahoma City area as it is to look at a radar in Minneapolis. I can look at all of them just as easily, collect all of the data from them, and look around at any place we want to.
Can you maybe tell us something about why radar is so important on this? When you were talking earlier about different models, I was almost afraid to ask what a model is because I can hardly wrap my mind around the components that must be involved here. I mean, it's space weather, I would think, how the sun's reacting and things happening on Earth and the jet stream.
Well, for the weather models, actually, they're at one level they're not that complicated. Now that's a that's a loaded word, relatively
thing,
speaking.
yeah.
Essentially all we're doing is we're solving the equations of motion. Go back to Newton's law of force equals mass times acceleration. Now, how do you define the forces? That's the hard part, and we have to keep track. The thing that makes a weather model really special, in some sense, we have to keep track of water. The atmosphere is an interesting place because we have water that's ice, it's liquid, and it's gas. And so we have to keep track of all of those things. And we essentially solve a set of equations that approximate from a grid point to grid point and from time step to time step. And we just sort of do this very, what at one level is an easy thing to do, but when you actually get down to the details of making it run and making it run efficiently, it becomes pretty complicated.
Okay, if the difference between now and 25 years ago is that we can predict further out now, how far out could you predict 25 years ago with some confidence?
Well, it kind of depends on what you mean by how good they were.
Okay.
We probably have pretty good confidence in the forecast. Maybe out to 2 or 3 days they were pretty good. Now we're probably looking at, for some things we're looking at even out to 5 days, and for other things we actually can be going out 10 days to 2 weeks. It sort of depends on what detail you're looking at. If, for instance, you're thinking about, well, are there going to be thunderstorms in central Oklahoma, then that's something that's maybe a couple of days out, maybe 3 days out in some cases. If you're looking at things like, well, is there a large-scale trough in the atmosphere over the western part of the United States, which means that conditions are going to be pretty good for storms in Oklahoma, but it may be Oklahoma, it may be Kansas, it may be Texas. That we can do in many cases out to a week to 10 days or so.
Now, the technology that's made this difference is the use of radar? And
well, not really the radar.
Oh, okay.
It's essentially the fact that we're able to, with more computer power, we can start to we make things at higher resolution. And the other really big change that's happened in the models is that we now use techniques that we call ensemble techniques. We understand the fact that we don't know exactly what the atmosphere looks like at any one time, and we also know that our models aren't perfect. We don't resolve all of the things in the atmosphere. If you think about a thunderstorm, it's a relatively small thing. And even when our grid spacing is just a few miles apart, well, that means you've got maybe 1 or 2 grid points for a thunderstorm. But we need to know what happens with the thunderstorm. It moves a lot of water up and around and heat up and around. So we have to actually use things that tell us, well, this is the effect of the thunderstorm, even though we can't exactly see what the storm does. And so we now run, instead of running a single model, we'll run maybe, in some cases, up to 100 models, looking at with slight variations in the way they solve those equations and the parameterized things that we can't see explicitly, with slightly different initial conditions, and we're able to now get a probability of things happening. As an example, when we had the very heavy rain in Norman, where there was over 4.5 inches in just a few hours, while on average the models were saying we'd expected about 1.5 inches on that day, there were actually maybe about 20% of the models were saying we might have up to about 6 inches of rain. And the fact that extreme event, we could actually have some idea it might happen, that was a dramatic improvement in the forecast.
So for those of us who are neither mathematicians nor scientists, is it that you're able to take more information and synthesize it from more sources at once, and you couldn't do that 25 years ago?
That's one big part of it. We can take the more information, but we also can look at it on a finer scale. We can actually look at little points. And so instead of saying that Oklahoma City and Tulsa are exactly the same place, we now say, well, there's a whole bunch of places in between. And by doing that, we can start to see real details a whole lot better.
The nuanced information of more radars or whatever.
Well, and radar helps a lot. Where radar really helps is in putting out warnings and saying what's going to happen maybe in the next hour or so. Because now the fact that we can actually see what's going on in the thunderstorm and get an idea of how the winds move inside the storm, that's a huge thing. We've also learned over the years, we understand what we're seeing better. From all the research that's gone on, there were things in 25 years ago that we didn't understand nearly as well as we do now, and so something would happen you'd see something on radar, and you'd be thinking, well, I'm not completely sure what's going on there. Well, we've learned a lot of what those things are, and we don't get surprised as often as we used to be.
I seem to recollect that when you predict a hurricane or something like that, there's a lot of lead time. Just, I guess it's the nature of what it is. Tornado is pretty short, isn't it? What is it? Maybe just a few minutes? Or?
Well, right now what we have for tornadoes is, on average, if a warning is put out before a tornado occurs, it's about 18 and a half minutes. But one of the big things that's happened over the years, and this is in large part due to the Doppler radars, is that in the 1980s we only warned in advance on about 25% of the tornadoes. Now we warn on over 75% of the tornadoes, and if we restrict ourselves to the really strong tornadoes, the ones that produce almost all of the fatalities and most of the damage, for those it's maybe about 95% of the tornadoes are warned in advance.
Where's the technology likely to surge ahead in the next 10 years?
Well, with radar, we are actually close to being where we might even have one of the next big revolutions, and that's hopefully less than 10 years away from going in. And this is something called phased array radar. Currently
what's it, say it again?
Phased array radar.
Okay.
And it's old military technology, but the big thing about it right now, if you see radars in use now, they have this dish that spins, and they send out a little pulse of energy and listen for the energy to come back to them. Well, with phased array radar, there are no moving parts. That beam of energy is steered electronically. And as a result, you can collect information much more quickly because you don't have to worry about the limits mechanically of moving this big heavy dish and keeping it in the right place at the right time. And so we can, right now it takes us around 5 minutes to look at all of the atmosphere around us, around the radar. With the phased array radar, we can do that same thing in less than 1 minute.
Well, so where would you predict that weather prediction would be, say, in 10 years? What can we'll be predicting further out and with a lot greater reliability?
We're likely going to be predicting farther out. We're actually exploring some things now that'll maybe, for some features, extend our lead times for being able to talk about them from out to maybe even a few weeks for some aspects of the atmosphere that we can't do for more than maybe a week or so right now. We'll probably be able to issue warnings in a great deal more detail. The real revolution is probably going to be in how we express those forecasts. Because right now we know that it's not just the ability to make a forecast, but it's a way to be able to describe a way of what's going to happen that allows people to find that useful and make decisions with it.
The end result with the person that's safe and maybe houses.
And being able to make, in some sense, better decisions, being able to make, and finding ways that we actually know from lots of things from outside of meteorology that people's decision-making processes are pretty complicated.
I want to ask you about that, but before we move on to talking about people, is the pace of development in weather technology, is it in any sense driven by the changes in the weather? The fact that the world is very much aware that with global warming and so many other things, does that stimulate?
It probably doesn't stimulate a whole lot. The fact of global warming doesn't really affect our technology on the forecasting side, because in some sense, the reality of global warming doesn't affect my forecast today.
Yeah.
That's a fairly slow process compared to what's happening on the day-to-day weather.
Right.
And so we sort of have some research that goes on that weather front, and then other research that's going on to try to understand what the implications of global warming are for the weather. But in reality, if even 100 years from now, when things are going to be a lot warmer, I'm not going to care a whole lot I probably won't be around then, but I'm not going to really care a whole lot about what impact that has on the weather, because I'm going to be using whatever the state-of-the-art technology is to look at what's currently happening.
But let me press this point a little bit, though, because it seems to me that you all might, if you haven't come under pressure to this point, at some point you really could come under a lot of pressure, say politically. I heard a lecture a while back about the national security implications of global warming, where country after country was assessed in terms of the weather changes there, their ability to respond to those weather changes, and on an index, how that affected their security, and because they were allies, the United States' global security. It seems to me that those pressures could, at some point, become significant, where you all are being pressured to come up with information faster, more of it, I'm saying, just along national security lines.
Well, but that's still going to be, in some sense, I think, on a longer time scale than my weather forecasting concerns. I think we're going to be at a point where we're going to be potentially being asked about, well, what on average are things going to be like 10, 20, 30 years from now or 50 years from now. And actually one of the big places for pressure for that is actually coming from the reinsurance industry. That has to look out a long way for their planning purposes, and that they really care a lot about extreme events. The kind of the 1 in 100-year event is essentially where they make or miss their money, and so they actually are very concerned about these kinds of issues.
Right. Does it make you mad when people talk about global warming being a hoax?
Mad may not be quite the right word. A little frustrated because the notion that carbon dioxide will warm the planet has been around for over 100 years, and the basic physical understanding of why has been around for almost as long, and that we know that without carbon dioxide in the atmosphere, the planet would actually be below freezing on average. Mm-hmm. And so we know that it has an important effect, and that adding carbon dioxide, there's no question of what's going to happen. The Arrhenius, who is known most of the time for the pH scale, actually predicted in the 1890s that if we doubled carbon dioxide content, that the Earth's temperature would rise by about the same amount we currently think. The big thing was he predicted just before the invention of the internal combustion engine, and thought it would take us several hundred years to even come close to doubling carbon dioxide. So he didn't anticipate how quickly that was going to happen. But I mean, it's the carbon dioxide and warming of the atmosphere on a global average. That's fairly straightforward, and I don't think there's anybody who seriously questions it in the scientific community. The real question, and this is I think the hard question to answer, is I don't know very many people who actually care what the average temperature of the globe is. It's how it affects the weather for you on a daily basis, and that's a lot harder question to answer as to what the real impacts are.
I think people have trouble thinking about scientific questions which they probably have no orientation to begin with, and then if evidence and cause and effect relationships are spread out over decades and hundreds of years, I think people kind of glaze over a little bit. I think maybe that's where some of the hoax talk comes from. But I mean, isn't it a fact that the warmest years on record have been in the last 10, 20 years?
All of the warmest years, certainly probably for the last few thousand years on the planet, have happened in the last 15 years. And certainly in the instrumental record, which goes back to the mid-1800s, 14 out of the 15 warmest years have been in the last 15 years. And so that's...
And there's a chain of events that's setting into...
There's lots of things that we know. There's lots of evidence that
the polar ice caps are melting.
The ice caps, and the fact that the poles are warming, especially the North Pole, because we know that the North Pole and the South Pole will respond differently, but the North Pole is warming faster than lower latitudes. That's something that you would actually expect from carbon dioxide being increased. Mm-hmm. One of the things I think that makes that we've seen, if we look historically, there are parallels and non-parallels with this and the ozone depletion of the 1980s, and that there was at that time initially there was a lot of pushback on the science of the chlorofluorocarbons depleting ozone, and as a friend of mine once said, there aren't any winners when you deplete ozone. Skin cancer increases no one thinks that's a good idea. One of the issues and once there was a policy alternative in effect, once that there was an alternative to the chlorofluorocarbons, the pushback on the scientific basis just stopped immediately. With carbon dioxide, warming of the planet, there will be winners and there will be losers in that.
And we're not talking about hundreds of years. We're talking about within
a century.
Within our lifetime in some cases.
Yeah, I mean, there are certain things that we have to be very concerned about that you may not directly think of. One of them is, for instance, that sea level rise. One of the big issues, if you look at South Florida, isn't necessarily that it starts getting flooded, which will happen.
Isn't it about 7 inches since 1993?
Yeah, the sea level rise is increasing. But for South Florida, one of the big issues is actually salt water penetrating into the fresh water supply.
Right.
Before it starts getting flooded, they lose a lot of their salt water supply. For us in this part of the country, one of the big questions is the extension of the desert Southwest. How far east does the dry land come? And the notions of water resources and changes perhaps of variability of weather occurrences, rainfall and drought, that's a real big unknown, and that's a hard one to answer.
I've heard that by maybe 10, 15 years, the rise of the seas could be like a couple of feet. I mean,
It probably won't be that quick. By the end of the century, we expect
like
about 2 feet or so of sea level rise.
2099, something
Yeah,
like
yeah.
that.
By the end of this century, but one of the important things to remember is that it's not going to stop then. I mean,
Yeah.
that's a projection for 2100, but lots of things will be happening that will be setting us on track for even larger rises than that. And several feet of sea level rise. The highest point in the middle of Florida is something like 12 feet above sea level. You start really compromising a lot of things.
There are a lot of effects that come out of this. It sort of spirals, doesn't it? Because if there's more water to absorb heat from the sun, then I think that actually sort of adds to global warming.
Well, what the water vapor does, just like carbon dioxide, is it actually absorbs heat coming out from the earth. It's not so much from the sun; it's what it's what it absorbs coming from the earth, and essentially that helps warm the earth. One of the things that it appears in a lot of ways we're seeing, and in a lot of factors, is an increase in the variability of weather. For instance, we know that since the 1970s, the number of days with an F1 and greater tornado, the kind of tornado that will start to cause damage to anything other than a very flimsy structure. Back in the 1970s, we had about 150 days with at least one. We now have about 100. But we now have about 5 times as many days with a lot of tornadoes, say like 30 or more. So we have the same number of tornadoes per year, but we're having them more in outbreaks now.
And greater intensity, right? I mean,
No, we aren't seeing any changes in intensity in tornadoes. That's something I think the evidence is pretty good that we aren't seeing a change in the intensities.
It seems like I read something, though, that says that the days where we get 3 or 4 inches of rain are more frequent now.
Rainfall, yeah.
Yeah.
Yes. If you look in the summertime in Oklahoma City, the probability of 1 inch of rain, given that it rains, back historically was about 13% of the days that had at least 1 inch of rain, that it rained, get at least 1 inch. Now that's about 25%.
Okay, I want to open a different box now, and I think this will surprise some people to hear this. I'm kind of excited about opening it. Weather-ready nation. What does that mean to you?
Okay. Well, weather-ready nation is essentially an idea that we need to become, whether climate changes or not, whether anything happens or not, that we need to become a more resilient nation to weather disasters. If you look around, we have, just on a weekly basis, there's flooding taking places, there's drought taking place. How can we as a nation be prepared to where the impacts of those things aren't as devastating and aren't as difficult to deal with?
So I think you referred to this before. So if weather reliability, a prediction is getting better and better, it really has no impact if that information isn't getting to the end users, the people that are going to be affected by it.
It's all whether we have to get the information there, and they have to be prepared to make a good decision with it. If I, for instance, had a perfect system for tornado warnings, and I gave you, I never missed, and I gave you 10 seconds of warning, you might not be able to do anything with that information. Or you might live in a place where you just don't have any options, and I've just told you exactly what's going to happen, and there's nothing that you can do. So we have to have better predictions, but then we have to get the information to people, but we also have to have them in a position where they actually can do something with that information.
How far are we going to go with this? I'm gathering that maybe 25 years ago, your concern was just do the weather, get the prediction, get it right, et cetera. Now, it sounds like you're taking responsibility for me a little bit and the rest of us out there who need that information, how we understand it, how accurately it's transmitted to us, timeliness.
Well, I don't know if I want to take responsibility for you.
Okay.
What I want to be able to do is to help you take responsibility for yourself.
Okay.
And to make sure that that, say, as a field, we just don't decide, well, if we change the words we say in the forecast, that'll help you. Well, we want to actually find out before we make those changes, how do we need to say things so that you can actually use something with it. If we suddenly started making our forecast in Finnish because somehow we were more precise with it, that might not do you any good if you don't know how to speak Finnish.
I think this really is a different level of responsibility, though, that you're taking for the end users. It's one thing to get the weather right, but to think about how it's going to be transmitted and how deeply it goes into the culture and how much I'm going to actually comprehend and be able to use that information. Maybe I'm deaf, So having the radio or TV on doesn't necessarily do a lot of good. It needs to be communicated another way. That's just a whole, that's a bigger stage you're on now.
It's a different approach, I think. It's the thought that, to me, it's the thought that just making a forecast that resembles the actual occurrence of the weather isn't enough. We're trying to partner with, particularly with social science, lots of disciplines, to understand how, when we put information out, how does it get used? Because we all know that just providing more information doesn't necessarily mean you make a better decision.
Right.
If you think about when you go to the doctor, there are probably lots of things when the doctor examines you that he could tell you. Oh, you've done this, and this. Well, what he'll basically tell you is, here's what you need to do, and here's what you are doing right now that you need to change so that you're a healthier person when you come back to me the next time. He doesn't tell you all the thousands of things he notices when he looks at you and examines you. He tells you the things that are important and the things that you can actually do something about.
I've seen some other examples, I think, of this kind of thinking where a relatively focused, maybe even narrow field suddenly really broadens its parameters. And I think the commonality here is thinking of the end user. In engineering, I think they're doing something very similar to what you're describing.
Absolutely. I mean, we're attempting as best we can, and it's not easy for physical scientists frequently to make this change in their attitude. But we're trying to think about how people use and make decisions with our information, and recognize that just getting the forecast part right may not do any good for anybody.
Well, with that, we're out of time. Thank you so much. This is really interesting stuff. I love it.
Fantastic.
And thank you for being with us today. See you next time for more current conversation. Thank you for watching.